Uh, am I recording? Fantastic. Hello, everyone. Welcome to our part one of our PCB design workshop with Altium. And let's get started. So, bleh. What is a PCB? Any guesses from the crowd? Well, a PCB is a printed circuit board that provides physical support and electrical connections for your electronic components. So if you have ever if you ever made a circuit in class, if you've taken 1101 or 2101 or any of those classes, and you're like, wow, I wish I could make this circuit like in an appliance or in like a real application. Well, that's where you would make a PCB. After you design your circuit and after everything's nice and settled, you can basically have a very permanent version of that circuit instead of you tip it upside down and all the pieces fall out. So I brought these today, hoping there was more people. But if you want to look, here's the PCB. And for the people in the crowd, I'll give you a bit of backstory. These are little wristbands from this year's CES at the Delta keynote. And as you notice, there's a little PCB camera. There's a little PCB inside. There's a little flexible PCB. And what this does, it's able to wirelessly communicate with their like radio antenna, and they're able to use these to basically all light up the entire stadium all at the same time. So yeah, uh, you'll notice it's flexible and it's got lots of components on it. Hey, there we go. Yeah, you see LEDs, resistors, capacitors, all sorts of stuff. We'll be going into more of that today. But yeah, if you want to make like a real product, either you're like in manufacturing, you want to manufacture a real something to sell, or maybe like an actual project, you're gonna want to make a PCB. They're really the backbone of pretty much every electronic device you see these days. You want to make a real product, make a PCB. Now, um, now let's kind of connect the bridge from your schematic to what an actual PCB looks like. So you can see on the top left here, there's a kind of there's what we call a two-layer stack up. This is for a rigid PCB. So essentially it's two layers, means that there's two planes of copper that you can have basically your electrical connections on. And so you see in the middle, there's like a core, it's a dielectric that is kind of like an insulator. It's kind of like the main base of the PCB, really gives it its structure. And on the top and bottom, we have the two copper layers. And on to cover those, we have the solder mask to basically make sure that copper is not exposed like to the outside world, that kind of thing. Um, let's see. Yeah. And then the to go over a few terms, if you see on the top on the right here, we have our component that's a little resistor right there, and it's connected by what we call traces. These are basically the wire connections between components. There are these copper traces on this layer, and then covered by, of course, the silk screen, and then that's one copper layer. If you want to connect your copper layers together, you can use something called a via. A via is kind of like a drill through the breadboard, or not, through the PCB. And it's actually able to make these electrical connections between certain copper layers as you desire. There's what we call blind vias that end up into an internal layer. There's a through-hole via, very common, where it goes through the entire PCB. And then you have a buried via where it's nestled in between like the inner copper layers. If you have a PCB that has this many copper layers. So on the right, this is actually a 6 layer. No, sorry, 8 layer copper, 8 layer PCB, because of course the upper and bottom layers also count. And yeah, there we go. There's a lot of different types of PCBs. If you want to make typically an appliance, typically your most common PCB are these rigid PCBs on the bottom right here. They're rigid, they're made of what we call FR4. That's kind of like the material, the substrate in it. If you have a more, let's say, flexible application, you might use a flexible PCB, as I demonstrated with these wristbands here. And if you're trying to get into something like aerospace, you want to really minimize weight, you can make your PCBs out of aluminum. on the top right here. Also very common used for LED, like LED matrices. You can see for this one specifically, lots of LD, LD5, LD4, LD13, lots of them. And you can have tons and tons of layers. Earlier, we saw a two-layer PCB. It could even go up to 32 layers or more. You'll see things like driver boards or even like your GPU will be like a multi-layer PCB with multiple different paths for traces, that kind of thing. Multiple ground layers, multiple power layers. And finally, there's different copper thicknesses for each layer of copper. You can have 1 ounce, 2 ounce, 3 ounce, 4 ounce, etc. And what thicker copper layers do is that it actually makes it, you can think of it as it reduces the resistance of the trace because more copper is more, or thicker copper means more paths for the electrons to flow through. So if you're making like a power application, like you're trying to make a power PCB or a like trying to run like 5 amps, 10 amps of current, you're going to want thicker copper traces or thicker copper weights just to handle that current. Going into some common PCB terms, just so that we all know what we're talking about. Like I said before, via is a connection between two layers of PCB, typically a drilled hole. A trace is simply the pathway to carry those signals from component to component. And you can see they have thicknesses and they have widths as well. And you're going to want to change those widths depending on how much current's flowing through them. The stacker is what we call like how we're arranging the different layers. Like for example, if you have like an 8-layer PCB, maybe you might decide these two middle layers are power or these two middle layers are ground. And mainly for more advanced PCBs. The silk screen is what we call like the outer layer. That's just like ink. It mainly just shows like the different like symbols where everything goes, as well as like the labels, as well as other like markings you want to make on your PCB. The footprint is where the actual physical PCB component like goes onto the board. So you can see here on the bottom right, the footprint is actually marked out by this silkscreen trace. And this is like a 14 pin through hole, like a dips like a dip component, a dual inline layer. Yeah. And finally, net, for those who uh, may not have heard this term in your circuits class, it's simply the shared electrical node between two components. You connect them with traces. So you have two components connected together. You can call that middle like area. You can call that the net. All right. Next, we'll quickly go into like types of footprints. So you remember these components actually take up physical space on your PCB. And a lot of them are actually standardized to different sizes, and you'll see they have different names. So when you actually search for these components, like on DigiKey or on like your other component site, yeah, you'd be able to basically have these standardized footprints. What also means is that if you can also interchange components if they have the same footprint, especially like different resistors, capacitors, inductors, that kind of thing. Now, big picture idea. Why do we care about PCB design? Doesn't it not matter? Can't I just wire everything together and it'll work 100% of the time? The answer is no, not really. Like, let's say you make a really nice filter, you've simulated it on uh, whatever simulation software, uh, whatever it's called. What's that simulation software called? PSpice. You've done a beautiful PSpice simulation. You got 9 inductors all connected together, and then you build it in real life, and it completely fails. The reason for that is because when we have the theory in one direction, you have unfortunately the real life, what we call parasitics that happen as well. Things like different like parallel connections, things like even your vias, they all have little tiny capacitances, inductances, resistances. Your ideal wires actually have a couple milliohm of resistance, that kind of thing. And then your components aren't ideal as well. Your capacitors can get devalued if you put too much voltage on them, if you have them too hot, if you have all sorts, you have to deal with the real components, and it sucks. So we care about PCB design and how we exactly lay out everything because we want to minimize these parasitics. We want to minimize these like imperfections, and we want to account for all these real components, so we can make our ideal schematic actually work in the real world. So for some applications, it's a little more tolerant, but especially if you're doing more sensitive things like high frequency, you're doing like computation, you're doing communications, these things matter a lot. Yeah. So that's PCB design, and hopefully we can teach that today. Now, let's go into our software. Don't worry, there's not that many more slides left. We're using Altium today. Altium is what we call an EDA software, or electronic design automation. You may have heard if you use SolidWorks, that might be a different kind of design automation. I don't know. But what it does is it helps you design PCBs. Other EDA software you may have heard of, KiCad, Easy EDA, Tinkercad, and Eagle. Eagle is like one of the first ones. One of the it's really old. Also, people don't like it a lot. So we're going to use Altium today. Another alternative, if you are not a college student, is you can use KiCad. KiCad is free for everyone to use, and you can pretty much do whatever you want in it. We're using Altium today because Altium is really used in industry a lot, and it lets you do a lot of things that some things that KiCad doesn't do. We just want to go over the whole thing completely. Now, I just want to brief everyone on how Altium works. In order to make your PCB, there's four main documents. There's the schematic document. That's where you put the schematic on your, well, that's where you set up your schematic. You've already designed your circuit ages ago, and you want to make it on your PCB. And then you make your schematic document. And then of course, you have the actual PCB document. That's where your actual layout is going. That's what you're exporting to the manufacturer. That's where kind of everything is going. Now, there's two supplementary documents that go with this. There's the schematic library and the PCB library. Now, the schematic library actually holds the specific schematic components that goes on your schematic. So it's schematic lab, but yeah. That's where you'll actually, so if you have like a custom component, like a IC chip, or like maybe even like a four input resistor, uh, you have a maybe like a just some like actual physical thing that can't even be described as a component. You put that on your schematic library, and that really will describe mainly the pinouts. Now your PCB library describes the footprints, like we mentioned before. It stores all the footprints so that there's an easy way to basically collect them all. There we go. And if you ever want to make changes to your document, all you have to do is update your schematic document, and then you hit a button to update your PCB document. And then Altium will automatically figure out what wire is supposed to go where, and they'll help you out. But yeah, that's the crux of Altium, and we'll be mainly working with these four documents today. Finally, we want to get into kind of like the workflow. What does PCB design look like? Well, first you design your schematic for your circuit. Let's say you've gotten your schematic from a manufacturer, or you've already simulated yourself. Next, you're going to choose the right components for your project. And then there's a lot of components out there. We'll get into choosing what ones work best for you. And finally, and then next you would design your footprints for each component, depending on what you bought. You lay out your components on your PCB, and then once they're all laid out and everything's nice and good, you can send your files to the manufacturer. And that's it. That's all PCB design really is. And then, of course, there's lots of details that go into every step, but hopefully we can cover the first three steps today. Now, you might be curious, what are we making today? We're going to be making a buck converter. Very nice. Buck converter is essentially what we call a step-down converter. It's one of the step-down converters. It can take like any input, like a certain amount of input that varies in voltage, and it'll be able to convert that into exactly a different kind of voltage. Right? This is what we call a DC-DC converter. Some number of voltage in, DC, and we can get exactly, in this case, 5 volts DC out. Now, what's really useful about this is that a lot of your electronics, if you've used logic gates, if you've used Arduino, if you've used any electronic component, they usually take 5 volts. And if you're trying to make an embedded system powered by some external power supply, maybe the outlet, maybe you have a LiPo battery, you're trying to make a ground vehicle or a like light or air vehicle, and they're powered by lipo batteries or some kind of battery, you're going to want to get that 5 volts to power your circuit. And how do you do that? Buck converters. Yeah, and these are seen everywhere. And you'll have like 5 or 10 of these in one thing just to set all the different voltages, just to power all your different electronic components. And nice thing, if you are familiar with these kind of converters, they don't heat up like linear regulators. Linear regulators, they do the same thing, except they burn that power as heat. And what ends up happening is you waste a lot of energy, and also you get a very hot component depending on how much current you're drawing. These buck converters, they're what we call switching regulators. They switch from 0 to 5. You can think of them almost like your PWM signals, and they don't heat up. They're fantastic. So we'll be making a buck converter today. Here's actually the schematic pulled straight from the data sheet of our buck converter. Now, when you're making these kind of circuits in your projects in your real life, you have decades and decades of engineers smarter and better than you, at least for the time being, that design these circuits. So for now, we'll just use their advice. This is the circuit we're going to be making. It takes 8 volts to 28 volts input, and it gives you in this case, it's a 3.3 volt output. You can change the resistance value here and actually changes that circuit value out. So this circuit requires capacitors, resistors, 1 inductor, the actual chip itself, as well as 2 terminal blocks to do the input output. So actually, we'll be able to make that today. So let's actually open up Altium. Let me close all my documents. And we'll get started. So many of you have probably downloaded Altium, but you maybe haven't set your license yet. We can go here this is your profile at the top right. And you actually go to licenses and give it a moment. And you should be able to add your license from here. Either you connect to the local server, I think, and then they give you a code if you did the sign up for the education license. And yeah, you can see I have some expired licenses from before, and I got my latest one today. And yeah, that's license management. If you need help with this, you can DM me or email me, but for now, we'll go through that. Do you have your license set up?
Yes, but I have to press the use license.
That's right. There is a button that'll say use license. It'll use the license. And then if you press release, it'll undo that license. Does it say confirmed? Is it Altium? And make sure it's Altium Designer Professional. Is that right? Fantastic. Professional is the actual design license. Viewer is just like if you want to view a circuit or view a PCB, but you can't edit it. It's free. It's a free license because you can only view things. But yeah, that should be all you need. Well, go ahead and if you can see on the top, there's the tabs here. You can go ahead and close license management. And now you're back on your home screen. Now, Altium's it's got kind of things everywhere. But if you go to panels here at the bottom right here, that's where basically every single tab is. So if you ever are missing a tab and you're like, Ryan, where's this tab? I don't see it. You can check your panels button to open it up. So we're going to go ahead and open up projects. Let me close my current documents. Sorry about that. And then projects is where you actually see the project. You can go ahead and pin that down by pressing that pin button, and you have projects open. Does everyone have that open? Now, if you're opening Altium for the first time, it should say something like project group 1.dsm or something like that. Does everyone have that? All right, looks good. Now, this is kind of this is like your local storage, where you're storing all your projects in. If you notice here, this is because I'm part of NGCP. We have a cloud or like a workspace that's connected to the cloud. So if you're working in a project group that has the workspace functionality, you'll be actually able to share files between people. So that's actually something that KiCad I don't think can do unless you set up like a Git. Altium has that built in, which is really nice. Let's actually start our first project. Let's right click here, project group 1, and let's do add new project. If it pops up, and it pops up. Now you're going to make sure it's local projects here. PCB empty, an empty PCB. And you can name it, let's name it workshop. Let's name it workshop spring 2025. That is today, right? Yeah. And that'll make your project. This is a personal preference, mostly because I don't know how to use the constraint manager, but you're going to make sure this is unchecked. Unchecked constraint management. We'll go into more. I'll briefly summarize it now. That describes kind of the design rules for your PCB design. So let's say you have a certain manufacturer that you're using. We'll talk about what manufacturer we're going to be using today for this workshop. But they'll actually have files that you can download and install into Altium to automatically set those design rules. They're very handy. But if you have constraint management, it kind of ruins that. So we're not going to do that. So everything should be good. Parameters, no parameters, workshop spring. We're going to create that file, that project, give it a moment. And there we go. We have a little project here. You'll see no documents added. We're going to want to add those 4 documents we talked about today, or just like on that slide. So you're going to want to right click the project name, add new to project, schematic, PCB, schematic library, and PCB library. All 4 of those documents, you can go ahead and leave them open. 1, 2. You give it a moment. Sometimes it takes a while for it to load. Schematic library. Oh, yeah. And it actually opens up the schematic library tab. So you want to go back to projects at the bottom left here. You see it started to populate this area. And then finally, what did I say? PCB library? Yes. My hands are crazy. Go back to projects. There we go. So that'll be 4 different documents, and that'll be all the 4 documents you need to actually do the PCB design. So actually, for each document, you're actually going to want to hit Control S to save, and you can just leave the default name, or you can name it like workshop library, workshop schematic library. But I'm just going to really quickly just go to everyone. I'm just hitting Control S, or if you don't have a keyboard, File and then Save. That works as well. And you're going to want to do this pretty regularly, saving whenever you make any major changes, just for your own benefit, really. PCB, just PCB. Yeah, it's not PCB 3D. Yeah, schematic PCB, schematic library, PCB library. There's these other documents too. I can kind of go over them. PCB 3D, I'm not really too sure. I think it's like a 3D version of the PCB layout, but you can actually do that on the normal PCB document. The active BOM standing for bill of materials. If you're working in a more like corporate or like professional environment, you guys might have this kind of document to list the components you make, actually. So it basically organizes all the components you make, and you can actually export that and have your finance department order those parts for you, essentially. Draftsman, I'm not too sure about. PadVia library, I don't know. CAM documents are what you'll see once you start exporting files. So when you're like, oh, I finished my PCB, I'm going to export it so I can send it over to manufacturer. You'll get these CAM documents, but you won't be making them like that. Output job files, same deal. Job being the PCB manufacturing. Database link, I don't know. But yeah, we'll go ahead and make our schematic. So we have our schematic here. It should be this kind of like document. And if you're an architect, it kind of looks like a blueprint almost, with your title, names, etc. But actually, we can't make our schematic until we make our schematic components. And that's the nice thing about Altium is that you can make your own schematic and footprints, your schematic components and footprint components. So we'll actually switch over to schematic library. And on the bottom left here, schematic library tab as well. And you can, this is where we're going to be making our components. These are just the symbols for the components, and they'll be very useful for us. So let's go ahead and at the bottom left, hit add. We're going to add a new component, and let's make a resistor. Resistor. If you're in a corporate environment, there might be more standardized ways to name your items, but we'll name it resistor. So let's make a resistor. The main component of a schematic symbol are the pins, because the pins actually define where everything's connected. So we're gonna want to go ahead and go to place and then pin. And you can see, oh, there we go. I can place my first pin. Now you'll notice when I'm dragging, when I'm like kind of hovering it around, I haven't clicked yet. There's this kind of cross line, this crosshatch on the right side. That's where the actual pin gets connected onto your document. And then if you press space to rotate, you can rotate it around. So go ahead and spin it right round, baby. You know, we're gonna want to go ahead and place two components. Oh, I did that backwards actually. And you're going to want that cross hatching on the outside. You can do Control V, Control C, Control V, like any other document. And you'll notice we got our pins. If you click on the pin, on the side should pop up. I'm going to drag my screen over. The Properties tab. If you don't have your Properties tab, you can go to Panels, and there's Properties as well. And you can actually go ahead, since we're going to be using this a lot, go ahead and pin this tab to the side as well. Now, give it a moment to adjust. Bear with me. All right. And then if you have a mouse, go ahead and scroll. You can scroll to zoom in and out. You can hit Control Scroll to scroll in and out. You can do this on your touchpad as well. Kind of scroll in. And you'll have to give each of these a designator and a name. Now, for our purposes, a resistor is a resistor. The names, it's a non-polarized component. The pins don't really matter. So we can just go ahead and hit 1 and 1. This is pin 1, and this is pin 2. And we're going to name it 2 too. Now, if we want to clean this up a bit, we can go ahead and hide the designator. And we just have our pin names, pin 1 and pin 2. Now this is the part where a lot of people kind of get stuck on. They're like, oh, now I got to make the resistor look extra perfect. I got to make it look really good. You could leave it like this. The rest of the design is actually just for your own benefit, for benefit of other people working on your design. So let's actually go ahead and the thing about our components, we're going to want to keep it as compact as possible just to make wiring up the schematic pretty easy. So let's actually change that pin length to 50 mils. And same for this one as well. So if you scroll down a bit, pin length 50 mils. And you'll see you got these tiny little pins. Very cute. Now, if you're wondering what a mil is 1,000th of an inch. So 1,000 mils is equal to 1 inch. This is kind of the imperial system's version of millimeters, give or take, give or take. I think like 25.4 mils is 1 centimeter, something like that. But you can go ahead and now hit place, and now any of these symbols to make yours quote unquote schematic. We're gonna go with the line, and you can go ahead and click on the edge of that. Now, if you're noticing, wow, my grid doesn't align with the edge of that pin, that's because your grid is too big. You can go ahead and hit G to change your grid size. And you can see on the bottom left here, where it says grid, you see grid 10 mils, 50 mils, 100 mils. Let's go ahead and do 50 mil. And you can kind of start thinking about, oh, you can kind of start seeing, oh, I can make my schematic. Now, if you hit the space bar, it changes how it's wired up. Either it could be a right angle or a straight line. Now, for those of you who are in electrical engineering, you know that this PCB is actually this is how a resistor looks like that. And then you hit escape. There's your schematic. There's your symbol right there. Nothing crazy. And hit escape again. And actually, you can change the color of the line too if you want to make it stand out. Now we have our blue resistor. Space bars rotate. Space bars rotate. I don't know what R is. Oh, R. For those of you who aren't familiar with like, I guess this is for a lot of like Windows programs. All these tabs, they have a character that's underlined. They're underlined because you can press that button as like the shortcut, basically. So R is actually for reports. So if you want to, yeah. So yeah. Space bar is for rotate. And you can make your cute little resistor like this. Nice and yeah. And then, oh, forgive me. Our next steps on top of adding our resistor, we're going to want to give it a designator. Now, if you've looked at a PCB or if you have the PCB I gave you, saw it in person, you'll see that every component is labeled with a letter and then a number. So for our resistors, they're labeled R1, R2, R3, R4. Or resistor 1, resistor 2, resistor 4. Now, we don't want to go ahead and add that manually. So what we can do is go to the designator and do R question mark for the designator here, R question mark. And what that allows Altium to do is that they recognize the question mark and they go, oh, when the time comes, when we hit annotate, which we'll do later, we can fill in that component and we'll give it a number. That'll be fantastic. You can add a description as well if it's a more complicated component. But yeah, that's we made a resistor here. I'm gonna go ahead and make a capacitor. I'm gonna make a capacitor next. So capacitor right here. And you see I just hit add and made a new capacitor. Place, you can hit P for place, P for pin. Make our one pin here, one pin here. Gonna make the shorter, 50 mils again. And then the names seem about right. We can go ahead and hide the designators just to make our life easier. And let's make a capacitor component. Let's make a capacitor. So you can even press this line button here to make a line. And you can go in and a cool thing about when you're drawing these lines, this applies for a PCB document too. If you hit tab, it pauses the placement. It kind of freezes everything. So you can actually go ahead and change your settings while it's kind of frozen like that. So we can actually make it blue right now, and then we can make our capacitor. Those of you who know what a capacitor looks like, it's actually two parallel lines. Two parallel lines. Kind of lopsided, but we can kind of drag this over. Not like that. You can drag these like lines over and then make our capacitor. Of course, the designator will be C question mark. And make sure that these little white dots, that's where the connections will go. They're on the outside of the pin. So next, let's make an inductor. Same process. We place our pin down. Not like that, right here. P for pin. Now we were two pins. We're going to name it 1 and 2. Just 1 here. And the 2 here. Like that. Make them shorter. Let's say 50. You don't have to type in MIL. I'm just hitting 50 and then tab to fill it in. And if you guys are familiar with an inductor symbol, let's look up inductor symbol. It's kind of curl. It's kind of these arches. So let's make those arches. We can go to place, and instead of pin, we can do elliptical arc. So we kind of center it here like that. Let's make it this long, this tall, and it's gonna go from, I guess, here to here. That's not very good. How about this? We'll make a normal arc. Arc here, make it line up. Go from here to here. There we go. 1, same distance. 2, like that, like that. 3, like that, and like that. And, well, let's just connect it like that, shall we? Now, our inductor. As long as your pins are like laid out correctly, on the symbol doesn't. The specifics of the symbol don't really matter. Is the point I'm trying to get at here. For our designator, we're going to do L question mark? Yes, L question mark. Because L is the symbol for inductor. Let's see. So have we got our 3 main passives set up? Resistor for R question mark, capacitor C question mark, and inductor L question mark. How are we doing and how are we doing? The arc, we'll give you some time for the arc. They have a lot of settings. So you hit arc. So you can start with the size, and then it gives you the starting point and then the ending point. And then it's yeah, that's it. Yeah, size, starting point, ending, which is all you need for it, really. Of course, if you want to get more detailed, you can change the widths, you can change the angles, you can change all that stuff. But yeah, there's our component. But miss water.
Same.
Yeah, we're not done with the component stuff. Let's make our next component. How are you doing? Is everyone caught up? Michael, are you caught up? Okay. How about you? What's your name? Sorry. Steven. How are you doing, Steven? The arcs? Yes. Yeah, the arcs are if the arcs are too much for you, you can just do a line like that. It's close enough, am I right? But you don't have to do that. Place, arc, and then the size, starting point, ending point. And once you have one arc, you can copy and paste them over and over again. Just for just to keep people from waiting, let's go ahead and add the next component. Well, wait for these guys actually.
Yeah, well,
You want to help Michael out as well? Or are you working on the arc? Or have you got it? Okay, okay. All right. Let's get into our next component, actually. Yeah, let's get into our next component. Way simpler than the arcs. There'll be a terminal block. I could call it terminal block. And if you guys don't know what I mean when I say terminal block, um, they're basically these, if you've seen them before. They're like sometimes they're screw in, sometimes they're plug in, like the DuPont connectors. But these are really good for like just like transmitting, like making a really tight connection, transmitting a lot of power. You see like one of these, you just screw them in. They're really handy. If not, then there's also familiar if you're familiar JST connectors, also used for power often. DuPont connectors, you've probably seen these before on your Arduinos or your breadboards. These ones as well. But the main thing is that regardless of what component you're using, all you need are the connectors. So let's do this. Let's place our two pins down. Let's say here and here. Give it a good spacing. We'll keep them long. We'll keep them like this. Just rename them pins one and two. Designator two. Like that. Got our two pins, and let's just place a rectangle. So we go to place and then rectangle. You can go ahead and start with the bottom corner and make the full box. That's covering our pins here, which is funny. I think it's because I placed the pins first. There we go. Maybe not. I don't really like that. Let's do this. I'm going to delete these pins. You just put new ones down. Fantastic. Pin one and pin two. That's all you need, really. And if you want to add more detail, more descriptive detail, let's say you're making DuPont connectors, you can add like a circle to the middle of it to mark like, oh, this is one component, this is a second component, that kind of thing. But we don't really need that. Pin one and pin two. Because these will be two terminal connections because that's what you need for power. All right. Finally, we got to make our actual chip. Now, this is like the real beauty of Altium right here. So actually, we can go ahead and go to the website on DigiKey talking about that, or that where you can buy the component. So when you go on to DigiKey, let's say you searched up, oh, I want the TPS 54308. Usually, very often, they'll have the data sheet right here. And the data sheet will describe exactly what the component does, how it works, and very importantly, the pinout of the component. As we can see here, it's a six pin component. One, two, three, four, five. And they've mixed the order around on the schematic document, on the schematic symbol, just to make it easier to wire, easier to look at, really. So we can actually copy this and we can make that on our thing. Let's go ahead and do TPS 54308, I think. Yeah, 54308. Okay. And we'll start with our rectangle. This is just basic rectangle just to show this is what our chip is. Make it just wide enough so that you can add the pins. You want to add 3 pins on each side. I did that incorrectly. Remember, you want these like little white dots to go on the outside. So here, here, and here. Flip it over. Here, here, and here. Now we can make these shorter, 50 mils. Oh, not negative 50, 50 mils. 50, 50, maybe 100. 100's a good middle ground, I think. 100. The lengths are really just to make it easier to do. 100, 100, and 100. Now, the main difference between these and our previous passive components is like the designators need to correspond to the pinout, and the name corresponds to what they do. So we go look at our schematic. We see our top left one is pin 3, and it's called VIN. So let's go ahead and do that. So designator 3, their name is VIN. And we can go ahead and delete that or hide that designator. Similarly, this one is our ground, pin number 1. So 1, GND. Go ahead and hide that. And let's do pin 5, or enable pin, 5EN. And let's go. Our top right is pin 6. That is our boot pin. And you'll start to notice maybe if these lines are like too close to each other, you can actually just move your components and then drag that rectangle out just to make your life a little easier. Next is our SW, pin number 2, or switching. This is a switching voltage. This is pin 2, SW. Finally, pin 4 is feedback. Pin 4, FB. And that's actually, let's keep those designators shown just so that if you're trying to follow along here, you can see what corresponds to it. Oh, we lost some. Here. Okay. So we should have, well, 5 components, and then we have our default, which we can kind of delete actually. So we have 5 different components: our capacitor, inductor, resistor, terminal, and our chip. Now that reminds me about the designators. The terminal, we'll call it T question mark. T question mark. And our chip, we'll call it U question mark. U usually being whatever whatever IC chip is that you're using. So often you'll use U question mark, T question mark for terminal, or even, or resistor, capacitor, inductor, and capacitor. Now, once you have these all done, you can go ahead and Control S to save. And now your library is saved. Making good time. How are we doing? Let's see if we can't get all, let's get all five of these components made. Made and fab. Hmm. Yep. Two pins. That's it. Nothing fancy. Pin one and pin two. T question mark or designate. Stephen, have you got the components? Cool. Mike, how about you? Listen. Oh, well. Anyway, bought the hospitals. I was actually just right. We definitely just draw it. We start at the bottom of my content. That was a lot of like you just click to the bottom. So you can top end to the bottom. That's it. You have to go all matters. It doesn't matter, but you're gonna have to match the numbers with my numbers. Oh, you see, I have the numbers like differently arranged. It'll be easier for the schematic. If you want to swap those pins around, you can go ahead and do that. You can also big ones. But that's pretty good. Yeah, so go ahead and hit that pin button so you don't have to keep it. Make it a little wider. Yeah, change that designate to one. All right. If you're watching the recording, we might be here. Fourth wall break. Yeah, crazy. If you've hit this point, comment down below what your favorite dinosaur is. Let's see. Yeah, maybe to like 50. Okay. And then shout out to the Brontosaurus. Heck yeah. What is my favorite dinosaur? Right. I guess I'll go into a little more detail about, for the benefit of the people watching the recording, we are making the components right now. And later, once this is all set up, let's go through everything again. Designators, pins, all of that. Terminal, your chip. We're going to be placing these on the schematic. And it'll be pretty simple. Go ahead and yeah. And talking more about our actual circuit itself, for those who are curious, if you maybe don't know how one of these work, is that what it essentially does is it takes in an input and it switches from that voltage to ground very quickly. And then you can say that the average voltage is 5 volt. Now the thing is, your electronic components don't like that, right? They don't like 28 volts and 0 volts over and over again. So a lot of the circuitry, at least for like this, mainly this inductor here, is the inductor actually manages a lot of that current flow. And if you're like familiar with inductors, they're very resistant to current change. So when you have like that sharp drop in voltage, it's actually able to kind of balance it out, depending on how you value it. We're valuing it like this. This is yeah, this is for 3 volts. This is a 3 volt guy. And then a lot of these capacitors are kind of what we call filtering capacitors. So these input capacitors, there's a filter in a lot of the noise going in. So the what we call ripple voltage is like kind of like the sine wave up and down that amplitude. It needs to be below a certain threshold. So what these capacitors do is they kind of DC couple it to ground. So it makes it so that if the voltage is too high, it's able to accept some of that power. If its voltage is too low, it's able to bring back some of that power. It's meant to mainly like stabilize it. We're using two different capacitor values here because capacitors, depending on their value, uh, affect how the what frequencies get like filtered out. You can think of it almost like an RC circuit if you know about those RC filters. So yeah, C1, these like 1 microfarad, 10 microfarad, good for like the lower frequencies. If you're dealing with more high frequency noise, you're gonna want to go smaller capacitance sizes, zero point 0.1, 0.01. Uh, 0.01 really. Zero point 0.1 is like still mid-range. For those of you who don't know about our 8-bit computer project, we're using zero point 0.1 microfarad capacitors to decouple our chips. Next we have our uh, let's see. How are we doing? Thank you, Nathan. All right. Next we have our kind of this is like a voltage divider circuit. Kind of I'll include you in the conversation. Yeah, I'm explaining what the circuit does. These capacitors are mainly for like filtering like noise. They're using two different values to filter different frequencies. This is a voltage divider to kind of the it's to enable the actual buck converter. So it's taking that voltage and it's reading for a certain like threshold to reach. If it reaches above a certain threshold, if that V in is like pushed high enough, the enable will actually kick. It'll be able to start switching, which is they don't want to switch like a zero point 0.1 volt thing, or else it kind of breaks. Um, and also, it kind of informs the actual buck converter on what the voltage input is. Over here on the right, we have a voltage divider circuit here. And what this does is it gives the buck converter feedback on what kind of voltage is coming out. And so if it's outputting too high, then internally in this chip, it's going to bring it back down. If it's outputting too low internally, it's going to bring it back up. The inductor is to kind of yeah, it's to basically turn that switching back and forth, almost that triangular waveform, into a linear waveform for your electronics to use. More capacitors as well to turn that moving waveform into like a fixed 5 volt signal. And that boot is there just to boot it. Yeah. This is the schematic we're making today. If you want to change the voltage that comes out of this chip, what you do is you change this R3 component, this R3 resistor. I think the value is 13.5. Will give you a 5 volt switch. But it seems like everyone's got it now. All right, we'll move on to actually making our schematic. So we're gonna want to swap back to our schematic document. Or first, well, make sure you hit Control S to save your schematic library, and let's actually place our components down. So I'm gonna just go ahead and do it. You can hit again, places right here, and place part. Well, you place your parts together. Now you're gonna want it to kind of populate the side area. If it hasn't popped up yet, this should be the tab called Components. So if you don't have that, hit Panels and Components. Make sure it's pinned so you don't have to swap back and forth and back and forth. And go ahead and if you're looking at components, you're going to want to go to the name of your schematic library. In this case, it's schematic library number 1. You just see the components you made. So let's go ahead and place those down. We'll start with our terminal block. Now you'll notice It's kind of backwards, so we can hit space bar to kind of flip it back around. And we're gonna go ahead and start making our circuit. So we can put down our switching, our buck converter right here, our switching regulator, and we can go ahead and wire that up. And let's just place our components down. The two capacitors here, one here, one here, two resistors here, one here, and one here. Let's say a capacitor here, an inductor here, I think. Yeah. Let's go with two more capacitors here. Yep. And then four resistors. One, two, three for our voltage divider. Another one here. Let's move these up a bit. Let's move this up a lot. Move this here. And then another capacitor here for small values. And finally, our terminal block output right here. Well, that's the whole shebang. You can also look at this schematic here. You can see two capacitors here, two resistors here, capacitor, inductor, two capacitors, capacitor, four resistors, and our output. So this is what it should look like. Now you'll notice there's a lot of like errors. It doesn't look that good. We can go ahead and start working on that. For each component, at least our passive components, if you double click on them, the properties panel will actually just pop up. You can change the comment to be the actual value of that capacitor. Um, main design choice that we're going to make here is that all our capacitor and resistor values are going to be like different, but the symbol is going to be the same. Therefore, our footprint for each of these like components will be the same as well. So we'll make this a 10 UF or 10 micro farad capacitor. We'll make this one a 0.1 micro. We'll make this one 511K. This is mainly for our benefit. This doesn't really affect the actual PCB design. 511K and then the 105K. All right. This capacitor is a 0.01 micro. This inductor is 10 microhenries. So 10 micro again. These two capacitors are 22 micro. This resistor is 50 ohm. 50 ohm. 50 ohm. Nope, not like that. 50 ohm. This resistor is 2K. This capacitor is 75 pico. Nope. 75 pico. Nope. 75 pico. We've got a 100K and then a 22K. So we got our 100K. Finally, our 22K. And that's all our component values, actually. So, yeah, if you can read that. Now, if you've done schematics before, you also know that there needs to be, well, your ground symbols. So we can go ahead and hit place and power port. And you go ahead and place one down. Now, if you notice, it kind of looks like a T-shape. That is our power. But if you click on the style, you can change what it looks like. Let's make it power ground. And you can also hit spacebar to rotate it, all that good stuff. And then we're going to not call it VCC, but call it GND. Put one down here. And then you're going to copy and paste them, just click them everywhere. Now you'll notice they're in the right spot when there's like red crosshairs popping up. And then Control V again, because that shows that there's a physical connection. That or if there's like a danger bars. So there's our ground here. All right. Capacitor here. No, sorry. Ground here, ground here. Ground here, and ground for our terminal block. So this is the state of the schematic so far. Let me move this over. so that we can see better. You can kind of move things around as necessary. You can highlight the components, just kind of move them. It is kind of cluttered. Yeah. And what's nice is that the wires actually get drawn. For drawing the wires themselves, you're going to want to hit either place and then wire, or as you can see by the shortcut here, Control W. Control W allows you to place the wire and wire up the components like so. And you're going to want to make sure that it actually hits the component by making sure the red dot is there. Really, not like that. Control Z, Control V, or Control Z to undo if you've made a mistake. Let's do this. And also you can hit spacebar just like before to actually change how everything is wired like that. Boot. No, sorry. Our switching goes into the inductor. Our boot goes from the capacitor to that line. Inductor goes out to the 2 micro, the 10 micro, the 50 micro, and finally the terminal block. These get wired up. These get wired up. These get wired up. And this gets wired up. So that should be the schematic. Straight up. The 10 micro, the 0.1 micro, 1K, 105K, 1 micro, 10 micro, 222 farad, 50, 2K, 5, 49K, and the output. That's the schematic. And that's basically how you would wire up this kind of Buckenberg. Give you all a moment to do so. Control W. Or if you want to place anything down, you can always go to the place tab on the top here. And at 10, you can see all the different components to place down. So one of these is the parts. Another one is the power ports for the grounds. And of course, the wire. There's also some other useful things here, like if you go to directives, there is a no connection. That's useful for not generating like an error if you have a floating pin. Yeah. And that's our terminal. That's our schematic. Let's see. You want to make them, and of course, if you're not doing this for a workshop, but rather doing this for like an actual project, you're going to want to make these look as nice as possible. These schematics are typically, these are what you and the rest of your team, if you have teams or partners, to work on together. And of course, a confusing schematic that only one person knows is not very good. Yeah. Place components down. Yeah. How are we? Working on it? All right, all right. Chat. Chat. Does it matter which designation, what direction the designator is facing? They do not. Talking about designator, are you talking about these like C question marks? They don't matter. You can have them upside down if you really desired. Yeah, the number. It depends, but specifically for. Oh yeah, so if you guys are wondering, the pins are labeled 1 and 2, but for our capacitors, inductors, and resistors, they are non-polarized components. So we don't care what connection, what way they're connected. So for our purposes, it's okay. But if you were to be using polarized components like a diode or even a polarized capacitor, or even this chip, like this chip right here, the pins do matter. So you want to be mindful of that when you're wiring this thing. Before capacitors, they don't matter. They don't, capacitors, inductors, resistors. Yeah, yeah. How are we? I don't want to get too far ahead. Yeah. The squigglies, we'll get into that, but they are there for a reason, mainly because they still have question marks on them. So it thinks, wow, you have like five duplicates of the same item, but we'll fix that. We'll fix that. Just let me know when the wiring's when you're done wiring. Okay, Michael, how about you? How are you doing? What does that mean? We have the part. Did you finish making all the parts? Okay, you were able to place the parts down. You can go ahead and hit. So go back to that. So if you hit place here on the top, and then parts, what it pops up on the side is like this component tab, right? Have you got that? And then there's probably like a bunch of different tabs. You're going to click on your schematic library. So for me, it's labeled schematic library. And then
Pretty sure it's safe as well. No, one person. Oh, this thing else. Oh, right. On the test station, it was. Probably was. Yeah. Yeah. So the double except for everything else top down. This video is license. Yeah. There we go. Oh, that's interesting, right? It's good to. Just have to, take pictures.
all right. So something we realize is that if your library isn't updated, you can actually go here and hit refresh, and I'll actually refresh your libraries to make sure everything's updated. Yeah, it's pretty cool. And then this is a very common theme in Altium is that you have to, if ever to make a change in one place, you have to actually hit the update button so it's to update in a different place. Specifically, if you make a change in your schematic, you're going to want to hit the update button to make a change in your PCB design. Shall I move ahead? I'll move ahead. All right. Now you definitely have all these red squiggly lines because we've labeled them all question marks. We're going to go to tools, and in annotation, annotate schematics. Now we're actually can populate everything with numbers. Make sure everything's all on, and then go ahead and hit update changes list. And you'll see 16 changes made because there are 16 components. And you actually see what it's proposing to do. It wants us to label this to C6, C3, C2, C1, etc. And we can go ahead and hit accept changes, then maybe validate changes, and then execute changes. And it's all green check marks. And you'll notice, wow, it's all labeled C1, C2, C3, etc., etc. Now there is still that squiggly line. Let me check. Let's save. Uh, Oh, there we go. It all updated. Fantastic.
Is there like more shortcuts like group components?
Well, I mean, you just click and drag, I think. Yeah, there's not much. Where's the button to update it? To update the. Oh, was it to do the annotation? Or what? Back to end. So just read it, right? The annotation, you go to tools up here, and an annotation annotates schematics. Now, when it pops this up, it kind of describes all the different like ways you can annotate it. And of course, update changes list, accept changes, you can validate them, and then accept them. And then this should be your, this is a finalized schematic base. This is the one. 217, that's a good time. Pretty good time. I actually might be able to finish into footprints. I love this. Footprints should be easy. We'll take our time. Yeah. This can be a very complicated schematic, very simple schematic. And
That's way huge.
huh? I would say KiCad's, yeah, they make theirs user friendly because they're also kind of open source. They're a lot more user friendly, but of course, user friendly means less control for you, right? Like if you have a nice fancy GUI, you don't get to see all the workings in between. Like this is we are making everything. We are making the symbol. We are making the schematic. So it's as you get used to it, I would say this is fast. I would because the shortcuts are pretty self-explanatory, I'd say. Um, Now, alternatively, if you were to have a really complicated component, if you go onto DigiKey, often you can actually download their model. And that model usually includes the schematic symbol. So you see, you have SnapMagic and Ultra Librarian each have their own schematic symbol, basically. I won't get into downloading like those like manufacturer parts today. Uh, but typically they're all right, but they're usually automated. So if you want to make your own custom thing, it's good to know how to make them yourself, essentially, just for maximum. We'll go through the whole schematic. We got the input here, uh, two capacitors, voltage divider, enable ground, switching, inductor, two capacitors, uh, three capacitors here, two over here, 75K, P, and the ground. How are we? Nathan, how are you doing? Have you got it?
I'm done.
Okay.
I'm just stumping.
How about you, Stephen? Have you, how far are you done wiring?
Yeah. Yeah. I'm wrapping up. It's just
Yeah.
and touchpad.
It is tougher on touchpad. I don't have to say, I can't say anything about that. All right. We're on 1 more minute for our recording listeners. I apologize.
Is there a way to make a whole sheet big?
Yeah. Yeah. So if you want to make the whole sheet bigger, let me find it. I think it's project options. No, it's not. Bear with me for a second. Right click preferences, I think. And then schematic. This is our schematic settings. Sheet size, B.
Right.
Right click anywhere, preferences, sheet size. You can B, which is why you usually make your components like very small. In the interest of time, I'm gonna move on. Uh, that's fine too. That doesn't matter. Not real. Like it does. Like it literally doesn't. The only thing that you actually need for the schematic are the layout, the pins, and how they're connected. That's all you need. The rest is for documentation, for working together with other people. But like, it's not gonna throw you an error just because it's off the sheet. This is a schematic. It's decorative. Like if like the capacitor symbol doesn't matter. You could have made this like a smiley face. Like it doesn't matter. The pins are what matters. The labels are what matter. Yeah. Well, I mean, if it doesn't like it, then it sucks to be it. That's the thing about having this much control is that like no one's gonna stop you. If there's an error, you have to find that out yourself. There's none of that. That's not a thing. Anyway, hit Control S once you're done, and let's move on. So now that we actually made our schematic, we put it together. How do we make this on a PCB? Now, the thing that we're missing are the footprints. What do these components actually look like in real life? Let's find out. Let's go. Let's go searching. Let's go searching for one. All right. I got our capacitors here, and these will be ceramic capacitors. And let's choose our zero point 0.1 microfarads. So actually, I already have it set up here, but I'll go through it again. When you go on to DigiKey, they have an insane amount of parts. So actually, if you want to follow along with my web exploration, digikey.com, digikey.com. We're all on digikey.com. All right. Now they have tons and tons of parts. What we're looking for, let's look for capacitors. So typically they are called passive components, capacitors right here. And if you click on that, you can see that there's a huge number of friggin' 800,000 different capacitors. Let's go to ceramic capacitors. Ceramics are really good for decoupling, really, decoupling, which is what which is what we're doing, really. And then they have all sorts of filters to choose, like what settings, whatnot. We are going to focus on, well, for one, capacitance. So here on our capacitance filter, you can actually just type in 0.1 microfarad. And you can see it's filtered it down from 800,000 to 11,000. All right. Still not, that's okay. Now, what if we made the product status active? Just so that they're still being manufactured today. All right, like 10,000. Tolerance we don't really care about, voltage we don't really care about. Well, we do, but we'll see it doesn't really matter. Now, what we want to see is the package slash case. Like I mentioned earlier in the slide, these a lot of these components have different kinds of packaging. I'll go back to the slides actually. They're spent a long time. Yeah. And then, oh, I think I forgot to mention. There's really two main kinds of components. There's through hole and then there's surface mount. Through hole is when there's a big lead and you slot into a hole and you solder the hole up. Now, like if you look at this diagram here, what they did is they put the hole through like the pin, or like they put the pin through the hole, and they basically filled this entire hole with solder to make that electrical connection. Now, what they invented more recently, and by recently I mean 30 years ago or like 50 years ago, is surface mount. This is a very flat pad that is exposed copper, and you can just kind of lay your component on top, cover it in solder, and it's good to go. Now, if you look at the resistors on the sample, like on the little PCB that I handed out, these are 0603s, 0603 size. They're very small, very, very small. Kind of a pain to solder. What's a lot easier are these 1206 components. 1206 is actually small enough that you get all the benefits of, the SMD, but you can still use tweezers to hand solder them. So when we're looking for them, let's actually select our 1206, 1206 package. So you can see here 3216 metric, but 1206 referring to the number of mils. And if we do apply all, we can apply these two filters, actually three filters, the product status, the package case, and the capacitance. And we can see all the different capacitors that fit our needs. So many different manufacturers. We got Kemet, we got Samsung, we got Yago, we got Murata. Murata, where's and same thing for resistors too. Uh, but let's look at this very first one. Hey, it's 10 cents per capacitor. That seems okay. And let's click on that product. And they got these crazy, crazy product name. And you can see they got a million of them too. It's crazy. But you'll notice here's the pricings. If you buy one, it's 10 cents. But if you buy 10 at a time, they actually cut down the price not to 10 cents, but to 5 cents. So actually it becomes more expensive if you want to buy seven capacitors, it's actually cheaper to buy 10. Which is kind of like it's because of like the way they do the packaging and like the cut tape, that kind of thing. And also like the distribution, but yeah, that's a funny little quirk about these components. And let's look at, well, what we're here for, the footprint. So if we click on the data sheet, we can see all the different stuff. And just to go over really quickly, these things can handle 50 volt. I think our maximum input was like 30 volt, uh, like 28 volts, so not an issue at all. And the tolerance we're not worried about either. We're not doing RF, we're not doing audio. So like these kind of wide tolerances on the capacitors, we generally don't mind. So let's look at dimensions. We got our dimensions of the actual part here. That's cool to know. What we do also care about is we go down all the way. Going to, is this it? Yeah, the footprint. So what they're calling the land pattern, what the capacitor is landing on. And so for our 1206 component, these are our dimensions for the for the pads. So as you can see here, they labeled it C, Y, and X, V1, V2. Lots of different guys. All right. So going on to this grid, grab a marker. So we should have two rectangular paths. See our screen. Can you see? Yeah, you guys can see. All right. What we care about are a few different measurements. We got our x here, which is equal to, wait, 1.70 millimeters. 1.70 millimeters. Units are important. Our width, or y, is 0.95. 0.95. Finally, we want the distance from the center. So actually, they very kindly worked it out for us. Some manufacturers will actually make you do the math. But this distance is 1.40. 1.40 millimeters. All right. So that'll be like the footprint we'll use for actually let's use density level thing. It's a better. That's all right. We'll do it like this. This is for density. You'll notice on this data sheet, they actually have three different sets of like pad layouts just for like how dense you want it. I chose least density, but honestly, if you have the space, most density is probably the best. Let's see. So, well, and then what's nice is that since this is a standardized layout, 1206, we can just use this layout for also our resistors as well. So let's do that actually. So let's move to our PCB library. New document, PCB library. Crazy, right? And our tab will be PCB library. This is where you set up your footprints. So we'll go here. Add. Oh, well, or not. We can delete that. We can double click it or we can right click it to grab the properties. Let's name it 1206. Or you can call it resistor. You can have different, depending on the components you choose, you can have different footprints for each component. For simplicity's sake, today we're going to be making the same footprint for all our passives. So we're going to do what we call, actually, this is not what we do. Sorry about that. Go ahead and you can, you don't actually have to name that. What we actually do, we go to tools and we go to something called the footprint wizard. For beginners, for us, this is the easiest way to do it. Footprint wizard. It'll do the pad layout for us, at least in a preliminary sense, and then we can edit it as later. But yeah, footprint wizard. So tools, footprint wizard. And we got the footprint wizard out. All right. Hit next, and you'll notice I have a bunch of different components. And some of these are like really crazy component. Well, some of these you could go over dual inline package. So if you worked with the logic gates, like the 7400 series, that's what these are. So these are through holes, and they'll lay out the holes for you. But what we want are, well, resistors. Well, capacitors really, but resistors. The main thing is you want to choose a pattern that matches what you're doing. So even if you're not doing a resistor, you could still choose the resistor layout just because it's two pads. Makes the most sense to me. Let's do millimeters because our manufacturers kindly gave it to us in millimeters. And we're going to choose surface mount technology. So these are going to be laid on top, and you're going to have to do a little careful soldering when you're putting this together. What's our pad size? All right. Well, we just figured that out, didn't we? The height is 1.7 millimeter, and the width is 0.95. Pretty good. And what are the distance between the two pads? Now, what they gave us was the distance from one pad to the center. So do some math in your head. You got to double this value to get the distance between the two pads. So this would be 2.8. And you'll notice the diagram has like the hatch marks to show what exactly the dimension you're measuring is. 2.8. The outline dimensions, we don't really care. That's just for the silk screen. And we're going to call this 1206. 1206 resistor. How about that? The wizard has enough. Let's finish it. Let's go ahead and delete our other one. And that's the footprint. Like that's what it is. And you would place your resistor slap dab in. Now, actually, if we want to place a resistor slap dab in the middle, you can actually adjust the size of this silk screen in order to make it in the middle-ish. Um, yeah. We didn't go into the layers yet, actually. But I can drag it. Thank you. Jesus. What? There we go. Whoop, whoop. Kind of estimate it. Actually, if you were to do this, you should actually look at the actual dimensions of the resistors, so you have that perfect like pad landing pad right there. But maybe something like this. Maybe we'll make a box that goes on the outside. Just to really encapsulate. Don't do that. If you move something accidentally, Control Z is your friend. And then, yeah, good enough. Good enough for the workshop, but preferably you're more precise on your actual project. Now, um, now let's go into the different colors. There's a lot of different colors here. Red is the top layer. So depending on how many layers your PCB has, there'll be different colors, but typically our top layer, we'll be using red. And you can even see the pad numbers, pad number 1 and pad number 2. That's really handy because that will be able to match with our schematic symbols. And then the yellow line, that is what we earlier called the silk screen. It's the outer ink layer that's not conductive at all. It's just there to really help us lay it out, or like know where each component goes. So once we're done, we can hit Control S to save, and we have our footprint. Now let's go back to our schematic library. Now, and let's think about what components do we want to have this footprint? Probably our capacitor, right? So let's go to our capacitor. And if you double click on the capacitor right here, the parameters pop up down here and it actually shows you the footprint. Oh, there's no footprint. We got to add the footprint. So let's drag out the tab a little more and drag it down. And it should pop up a button right here that says add. If we go to here and add footprint, and then we can browse and go to our PCB library, and you can pop up the exact footprint that we want. Hit OK. Fantastic. Let's go to our resistor now and do the same thing. Add footprint 1206. There we go. All right. Now let's talk about our terminal block. Not that. That is my ASUS. All right. Bear with me. Okay. If we look at a terminal block, actually, I have one linked already. Or I don't. Okay. Don't mind my search history. Terminal block. Sure. Oh, that was just now, actually. Here we go. So let's go to, we search up terminal blocks on DigiKey. I'm sure you can do it yourself. I don't need to walk you through it. But these terminal blocks are through-hole components. They have a stick, a little pin that goes out the bottom. So we're going to want a footprint that matches that, a little space for the pin, essentially. Now, what is the spacing between this pin? Well, they label it here 5 millimeter, but let's actually look at the recommended layout here. So here we have the data sheet by the supplier, and you'll notice from pin to pin, it is 5 millimeter from the center to center. And if you were to really work on your footprint. You can add the outline as well, do all the measurements. But we'll go ahead and do this really quickly. Go to our PCB library and you're gonna hit add. Well, actually, my bad. Not hitting add. Going back to the footprint wizard. We love the footprint wizard. And even though this is a terminal block, we're gonna use resistors just because they're two components. 5 millimeters, we're going to keep it in millimeters. And we're going to be through hole technology. The size of the pads, let's look here. They recommend 1.3 millimeters of the this symbol means the diameter. So 1.3 millimeters of diameter, which is to give it enough leeway because the pin itself is actually 0.7 millimeter, but typically your pads and your holes are bigger than the actual component so that they can fit. So what I say is 1.3. And in our outline, our actual like this is the actual metal where you're able to add solder. You're gonna want to typically you want to double the diameter of the pad. So 2.6 for everything else. 2.6. So 1.3 hole size, 2.6 width. And then what this looks like, if I go look up like through hole PCB, what we're talking about is the actual like metal on the outside right here. So you can see like they have a like an axial resistor right here, and the actual pad, quote unquote pad, is what allows you to put solder on and get that component onto the board. So how should pads be positioned relatively? Well, you said 5 millimeter, or you said number 5. Height and width of the outline we really care about. And the name, we're going to call it terminal block. Next, and then finish. And that's our footprint. Now, the actual outline doesn't actually match our footprint. So you can go ahead and like edit it if you wish, make that box a little bigger, or if you were to do this on an actual project, make the outline exactly what the box will look like once it's placed on. So I'm being kind of callous here. Doing it like this, that's our terminal block. And you're able to slide this right on. So go ahead and Control S, oops, Control S, and then go to our schematic library, terminal block, add footprint, browse, terminal block. There we go, terminal block, nice. Okay, all right. And I think I went a bit fast. I might have went a bit fast, but the process is the same. All right. Email. Someone got a letter. Now, well, pretty importantly, let's look at our actual buck converter. Our buck converter's got a footprint as well. If we look at our layout, typically, well, TI Instruments pretty good about this. They'll describe to you how they want you to lay it out. Well, that's one way. Let's go look at the packet. Let's go look at the actual name of the package. They are where we are using a SOT 23 package. So I think if we were to go to the footprint wizard, actually, I haven't tried this. SOP. Yeah, SOP. This is SOT. Should be the same though. Hey. Dimensioning. This is layout, but did they have the pin out? Oh, here it is. Yeah, just keep going down. So here's like the actual component itself, and here's their recommended land pattern. So you can see there, they gave us a lot of numbers. This is all in, I think, mils. What's our dimension? Millimeters? Yeah, sometimes they're not very good about that. The wrong dimension. And it really does matter. A mil is very small compared to a millimeter. Yeah, all right. We'll go into Altium. Let's pick, yeah, not the dual outline package. Let's pick the small outline package. Keep it in millimeters. Does that make sense? 1.1 millimeter? Honestly, yeah, that's the size of the component. All right. What is the size of each pad? Zero point 0.6 by zero point 0.1. So 0 0.6, 0. Did I say 0.1? 1.1. Sorry. 1.1. 0 0.6, 1.1. That's each pad. The pads should be spaced. Let's look at it. 0.95 parts. So 0.95 apart. And on the top, 2.7. 2.7. All right. The width of the outline, we don't really care. Now, how many pads should it have? That does matter. This is a 6-pad device. 6. So 3 on each side. Well, we're going to name this TPS 54308. And there we go. Yeah, nice. We can make our outline look a little better. It is just a really quick and easy way to get the component onto the board. There's a lot more, like Altium has so many different features. This is just a really quick way to get it. And there we go. There's our pad. And we can even, if we were dubious about the size, you could go to reports and measure distance to actually measure the distance between the different components. So they give us to mils. I think if you hit Z, Shift Z, no. I'm gonna change units. Shoot. Oh, Q, sorry. If you hit Q, it'll actually toggle between mils and millimeters. There we go. And Shift C to clear that. And that's our TPS footprint. Control S. And let's upload that to here. Add footprint. Oh, here, this is another button down here. Add footprint. Let's add footprints. If you can't tell, I'm getting tired. Footprints. No footprints. Control S to save. Looks fantastic. There we go. Let's see. Now we're missing the inductor. The inductor needs a footprint as well. Now, what inductor are we using today? I actually got it right here. You need an inductor that is 10 microhenry. You also need an inductor that can handle the amperage. So this is a 3 amps. So we have this fixed inductor here, 10 microhenry. We can handle 10 amps. Very fantastic. Borns, love Borns. Coil, or another manufacturer that's cool is Coilcraft. If you, they make some crazy inductors, and they actually gave us a very easy layout. Two pads. Give us the distances. Very nice. Let's go make that. So PCB. Let's do our footprint wizard. Now again, since this is a 2-terminal device, we can just use the resistors again. Let's use, what's an easier move? Easier to use millimeters. Let's use millimeters. These are going to be surface mount, of course. And let's look at our pad dimensions. It's going to be 4.5 by, ooh, now they want you to do math. If this distance is 15 and this inner distance is 7, what's the length of the pad? This is the quiz. Go back to algebra 1. Go. 4. That's right. It's 4. It's 4 here and 4 there make 8. So we're going to go 4 millimeter by, what did I say? 4.5 millimeter. These are way larger compared to our resistors. These are some beefy inductors. How should they be positioned? Now that's a little more trickier. If our inner distance is 7 and each pad is 4 and the centers of each pad is only 2, if we're actually adding 2 on each side, that would be not 9 but 11. So from this center to this center is 11. Are you convinced of that? Additionally, you can add these two together. 15 plus 7 is 22, and you divide by 2 to get the average length. That is 22. So 22 millimeter. 22 millimeter. Let's say I don't put units because I'm cool like that. For real, for real. Outline we can change, but that's default. We'll call this inductor. What?
No.
Yes, you're right. Oops, it is 11. I forgot to divide by 2. You're right, you're right. This should be inductor. Next, and then finish. That is our inductor layout. Now, if you look at the actual dimensions of the inductor, it's actually this big box. Like, looks like this. So just like roundabout, like we're not being exact here today, but in your project, you would want to be exact. Control S to save and go to your schematic. Inductor, add footprint. Inductor. Okay. Okay. Control S. And this is one of the more important bits. When you make any change to your PCB library or schematic library, and you need to update your currently existing schematic, like I mentioned before, you always have to update. There's a button to update, and that button is actually your right click, and you hit update schematic sheets. Schematic sheets. Just right click on the project right here. Update schematic sheet. You can just like on this like area here, and you see it says updated one component. Terminal block. You're going to update that component. TPS, update that component. Resistor, update that component. Capacitor, update that component. And what that does is it updates every single component that's on the schematic. Hit Control S to save. And if you look at the actual components, they have footprints because we updated them. We were able to add the footprints to them. So now our schematic is now we're really done. Then we got the footprints, we got the schematic symbols, we had everything. Now that was all I needed to cover today. But let's do the next step. Once you have your schematic, all the footprints are laid out. Design, update PCB document. Again, whenever you want to make a link between documents, gotta hit update. Hit update, and they have this whole thing. It's called the engineering change order, ECO. And it's all the things that you're wanting to add, subtract, change to your schematic or to your PCB. But for us, it's just adding everything. So we look through it, looks about right. We validate the changes to make sure everything's green, and then execute. Oh, sorry about that. Design, update PCB document up here. On the top. Update PCB document, validate, and of course, biggest change, execute. And you check to see everything's done. And now let's look at our PCB document. Whoa, there's our components. They're all bunched up over here. But there we go. That's how you get from the schematic to the actual PCB layout. So you can move your components around, kind of like juggle them around, check them out, see what they do. And what you'll notice is that because of our schematic, they actually draw lines between all the traces, between everything that needs to be connected. So you can see, wow, look, that's the switching pin right there connecting to our inductor, just like how we have the switching pin right here connecting to our inductor. So it's all laid out. It's all beautiful. Now we do have 5 minutes left. So we're going to go into the PCB layout next week. This is just really all the steps up to the PCB layout. There's a lot to go over for PCB layout. But you'll notice that these labels have names. And these are the nets that we were talking about. And a lot of these resistors, they already have the ground net label. But these other nets, they're like kind of default net. They're like net for capacitor 4, number 2. Like it's really hard to read, and it's hard to tell what's going on, especially when you have a lot more components going down. So let's go back to our schematic document and let's add labels to all our nets. So let's say our input, we can, like we do is place. Instead of any of these parts, we add a net label. And we can add a net label to, let's say here, this is our V in, voltage input. And similarly, if we place a net label, over here is our V out. V out. We can have more labels here, like our. Not everything needs labels, but often your ICs having labels are really useful. This is our feedback, our FB here. And especially when you have multiple components connected to something, it's easier to tell. Instead of having to check the numbers, like which number is which. So we place another net right here. That's our switching, so SW. And then the rest we don't really need. You could put one here for enable. Basically, if you have like general rule of thumb, if you have three or more connections into a single net, it's way easier to have a label to make it like easy to read. So there's EN right there. And then of course, and then once you make that change and you save it, you're going to want to update your PCB document with those changes. So validate those changes, execute the changes, and close. And now if we look at our, let's say our inductor, before it used to say net C1 underscore 2, net C5 underscore 3. Now it says an actual descriptive label that we can use. Our the switching input, and then our V out. And then that goes for our buck converter as well. All of these are labeled. Very nice, very pretty. As well as our terminals. Our terminals are labeled V in and ground versus V ground and V out. So this is, and you can also just highlight everything and just drag them over. Now, now this is where the fun begins. This is where the PCB layout begins. Now you can actually start moving things around and connecting them with traces. Now we are reaching the end of today's scheduled programming, but that's the first part of using Altium. Getting those parts together, getting those footprints, getting those real life connections together to start making our PCB. And next week, if you want to join us, we'll be going over general PCB layout as well as really critical PCB fundamentals to minimize those parasitics, minimize errors, and also make sure your PCB is fit for the application you're trying to use. We'll also talk about manufacturing, getting those files sent out, as well as some possible manufacturers to use. And yeah, hope you enjoyed today's workshop, 2-hour segment. If you haven't already, please sign in on the QR code right there. And we hope you enjoyed. That'll be it. I don't know any of that. Thank you. Thank you for coming. I will be ending the recording now, and I will be uploading that to our IEEE YouTube channel if we have that. I hope so. And then, yeah, if you're watching this in the future, hello, future. How are y'all doing? Thank you.